Good evening, and thank you for joining me. Tonight, we'll embark on a serene journey to the moon, uncovering fascinating facts about our celestial neighbor. As we explore the mysteries and wonders of the moon, let the gentle rhythm of these facts guide you to a peaceful slumber. Imagine the cool, calm lunar surface, the soft glow of moonlight, and the vast, tranquil expanse of space. Allow these soothing thoughts to quiet your mind, helping you drift into a restful sleep. Now, let's begin our journey to the moon. 1. The moon is Earth's only natural satellite and the fifth largest moon in the solar system. Its presence has significantly influenced the development of life on our planet, affecting everything from the tides to the behavior of nocturnal animals. The gravitational pull between Earth and the moon stabilizes our planet's axial tilt, leading to relatively stable climates over geological timescales. 2. Measuring approximately 3,474 kilometers (2,159 miles) in diameter, the moon is a fascinating object of study. Despite its smaller size compared to Earth, its relatively large size compared to the planet makes it unique among natural satellites in the solar system. This size ratio influences the moon's significant gravitational effects on Earth, contributing to ocean tides and even slight changes in Earth's rotation. 3. It takes the moon roughly 27.3 days to complete one orbit around Earth. This period, known as a sidereal month, is crucial for understanding the timing of lunar phases and eclipses. The moon's orbit is not a perfect circle but an ellipse leading to variations in its distance from Earth, which in turn affects its apparent size in our sky. For, due to a phenomenon called tidal locking, the same side of the moon always faces Earth. This synchronous rotation means we only ever see one hemisphere from our vantage point. The far side, often inaccurately referred to as the dark side, receives just as much sunlight but remains hidden from view, adding an element of mystery and intrigue to lunar exploration. 5. The far side of the moon, commonly called the dark side, is not perpetually dark. It experiences day and night cycles just like the near side. This misnomer stems from the fact that it remains unseen from Earth, leading to early misconceptions. Modern missions have mapped this side extensively, revealing a terrain markedly different from the near side, with more craters and fewer maria, or large basaltic plains. 6. The moon's surface is pockmarked with craters formed by asteroid and comet impacts over billions of years. Unlike Earth, the moon lacks an atmosphere to burn up incoming objects, resulting in a heavily cratered landscape. These impact sites, varying in size from tiny pits to vast basins, offer clues about the history of the solar system and the frequency of such collisions in the past. 7. Without an atmosphere, the moon has no weather, wind, or precipitation. This lack of atmospheric protection also means that the surface is bombarded by meteoroids, cosmic rays, and solar radiation. The absence of weathering processes preserves surface features for eons, allowing scientists to study the moon's geological history in great detail. 8. The moon's gravity is about 1/6 of Earth's gravity, creating a unique environment where objects weigh significantly less. This reduced gravity has profound implications for potential future lunar exploration and habitation, as it affects everything from human movement to the operation of machinery. Astronauts visiting the moon must adapt to these conditions, which can be both freeing and challenging. 9. The moon experiences extreme temperature fluctuations, with daytime temperatures soaring to 127 degrees Celsius to 160 degrees Fahrenheit, and nighttime temperatures plunging to minus 173 degrees Celsius to 180 degrees Fahrenheit. These harsh conditions result from the lack of an atmosphere to regulate temperatures, creating an environment where thermal management becomes a critical consideration for any lunar mission. 10. During a lunar night, which lasts approximately 14 Earth days, temperatures can drop to a frigid minus 173 degrees Celsius to 180 degrees Fahrenheit. This prolonged period of darkness and cold presents significant challenges for future lunar habitats and equipment, which must be designed to withstand such extremes. Managing energy and maintaining warmth are crucial for ensuring the safety and functionality of lunar operations during these extended nights. 11. The Moon's surface is covered in a fine, powdery dust known as regolith. This dust, created by billions of years of meteoroid impacts and space weathering, is composed of tiny fragments of rock and mineral particles. The regolith poses unique challenges for lunar exploration, as it can be abrasive and cling to surfaces, potentially damaging equipment and spacesuits. 12. The Moon has large, flat plains called Mare, which are Latin for seas. These dark basaltic plains were formed by ancient volcanic eruptions that filled large basins with lava. When observed from Earth, the Mare give the Moon its distinctive man-in-the-moon appearance. The smooth surfaces of these plains contrast sharply with the rugged highlands and cratered regions, offering insights into the Moon's volcanic past. 13. There are over 300,000 craters on the Moon's near side alone, each telling a story of cosmic collisions. The largest crater, the South Polaican Basin, is about 2,500 kilometers, 1,550 miles in diameter, and 13 kilometers, 8.1 miles deep. This immense impact structure is one of the largest in the solar system and provides a window into the Moon's interior and early history. 14. The Moon has no liquid water on its surface, but evidence from lunar missions suggests that water ice exists in permanently shadowed craters at the poles. These regions, shielded from the sun's warmth, offer a cold trap where water molecules can accumulate. The presence of water ice could be a crucial resource for future lunar missions, providing drinking water, breathable oxygen, and even rocket fuel. 15. Lunar eclipses occur when the Earth comes between the Sun and the Moon, casting a shadow on the Moon's surface. These events, visible from Earth, create a dramatic reddish appearance known as a blood moon. During a total lunar eclipse, the Moon passes through Earth's umbra or central shadow, resulting in a spectacular and eerie transformation of its color. 16. The Moon has a very thin and tenuous atmosphere called an exosphere. Unlike Earth's atmosphere, the lunar exosphere is composed of sparse particles that rarely collide. This near-vacuum environment means that the Moon's surface is exposed directly to space, influencing temperature fluctuations and the behavior of dust particles. 17. The concept of a blue moon refers to the occurrence of an additional full moon within a specific time period, typically a calendar month or season. This rare event has led to the phrase "once in a blue moon," indicating something that happens infrequently. The precise definition has varied over time, but the phenomenon remains a fascinating aspect of lunar observation and folklore. 18. The Moon's origin is widely believed to be the result of a giant impact hypothesis. According to this theory, a Mars-sized body named Theia collided with the early Earth about 4.5 billion years ago. The debris from this catastrophic impact eventually coalesced to form the Moon. This hypothesis explains the similarities and differences in composition between Earth and the Moon and has been supported by various lines of evidence from lunar samples and computer models. 19. The Moon has weak magnetic fields in certain regions, remnants of what might have once been a more substantial lunar magnetosphere. These localized magnetic anomalies are thought to be caused by the cooling and solidification of the Moon's core and crust. Unlike Earth's global magnetic field, these patches do not offer widespread protection from solar and cosmic radiation. 20. The Moon has a synchronous rotation, meaning it takes the same amount of time to rotate on its axis as it does to orbit Earth. This synchronous rotation results in the same hemisphere always facing Earth, creating the near side and far side distinction. This phenomenon occurs due to tidal forces over millions of years that have gradually synchronized the Moon's rotational and orbital periods. 21. The Moon's interior is composed of a crust, mantle, and core, much like Earth. However, its core is relatively small, making up only about 1 to 2% of its mass. The mantle consists of silicate materials rich in magnesium and iron, and the crust is primarily composed of oxygen, silicon, magnesium, iron, calcium, and aluminum. Seismic data from lunar missions have helped scientists understand the internal structure of the Moon. 22. The Apollo missions, conducted by NASA between 1969 and 1972, were the first and only manned missions to the Moon. A total of 12 astronauts walked on the lunar surface, conducting scientific experiments, collecting samples, and capturing iconic images. The success of these missions provided invaluable knowledge about the Moon's composition, formation, and environment, inspiring generations of space exploration. 23. The Moon has phases due to its orbit around Earth and the changing angles of sunlight illuminating its surface. These phases, from new moon to full moon and back, are a cycle that repeats approximately every 29.5 days. The phases result from the relative positions of the Sun, Earth, and Moon, affecting how much of the Moon's surface appears illuminated from our viewpoint. 24. The Moon plays a crucial role in controlling Earth's tides. The gravitational pull between Earth and the Moon causes the oceans to bulge, leading to high and low tides. The interaction of lunar and solar tides also results in spring tides, which are higher than average, and neap tides, which are lower. This tidal influence affects marine life, coastal ecosystems, and human activities along shorelines. 25. The Moon's influence on Earth's tides has slowed our planet's rotation over time. This gradual deceleration, known as tidal braking, lengthens the day by about 1.7 milliseconds per century. As a result, the Moon is slowly moving away from Earth at a rate of approximately 3.8 centimeters (1.5 inches) per year. Over millions of years, these subtle changes will have significant impacts on the dynamics of the Earth-Moon system. 26. The Moon has no breathable atmosphere, making it inhospitable for human life as we know it. Any future lunar habitats would require airtight structures with life support systems to provide oxygen, remove carbon dioxide, and regulate temperature and humidity. Advanced technology and careful planning are essential to create a sustainable environment for long-term human presence on the Moon. 27. The Moon's surface is covered with features called riles, which are trench-like structures that can stretch for hundreds of kilometers. These riles are believed to have formed from ancient volcanic activity and tectonic forces. They vary in width and depth, with some resembling river valleys and others appearing as narrow channels. Studying these riles provides insights into the Moon's geological past and volcanic processes. 28. The Moon has subtle but detectable seismic activity, known as moonquakes. Unlike earthquakes, which are primarily caused by tectonic plate movements, moonquakes can result from tidal stresses, thermal expansion and contraction, and meteorite impacts. Seismometers placed on the Moon by the Apollo missions have recorded these quakes, which vary in intensity and provide valuable information about the Moon's internal structure and dynamics. 29. The Moon's lack of an atmosphere means there is no sound on its surface. Sound waves require a medium like air or water to travel through, and in the vacuum of space, they cannot propagate. This silence creates an eerily quiet environment where astronauts on the Moon would only hear sounds transmitted through their suits or equipment, adding to the sense of isolation and otherworldliness. 30. The Moon's albedo, or reflectivity, is relatively low, meaning it reflects only about 12% of the sunlight that hits its surface. This low reflectivity contributes to its gray appearance when viewed from Earth. The albedo varies across different regions of the Moon, with the darker Mare reflecting less light and the brighter Highlands reflecting more. These variations provide clues about the composition and history of the lunar surface. 31. The concept of lunar gardening involves studying how plants might grow in lunar soil, or regolith, as part of future plans for long-term lunar habitats. Experiments have shown that while lunar regolith lacks essential nutrients found in Earth's soil, it can be amended with organic matter and nutrients to support plant growth. Understanding how to cultivate crops on the moon is a critical step towards self-sustaining lunar colonies, reducing the need for resupply missions from Earth. 32. The moon has been a source of inspiration for cultures around the world, influencing mythology, art, and literature. Many ancient civilizations created myths and legends about the moon, attributing it with divine qualities or seeing it as a celestial entity with powers over nature and human fate. This cultural significance continues today, with the moon featuring prominently in poetry, music, and visual arts, symbolizing mystery, romance, and exploration. 33. The lunar poles are of particular interest to scientists and future explorers due to the presence of permanently shadowed regions that may contain water ice. These cold traps, found in craters at the poles, remain in perpetual darkness, preserving ice that could be used for drinking water, breathable air, and rocket fuel. This potential resource is a key factor in planning sustainable lunar bases and long-term human missions. 34. The moon's surface is marked by several distinct features known as lunar swirls, which are bright, sinuous patterns of higher albedo material. These swirls are thought to be associated with local magnetic fields that protect the surface from the solar wind, preserving the bright material. One of the most famous swirls is Reiner Gamma, a strikingly bright and sinuous pattern that has intrigued scientists for decades. 35. Lunar eclipses have played a significant role in scientific discovery and historical events. For instance, ancient astronomers used observations of lunar eclipses to understand the relative sizes and distances of the Earth, Moon, and Sun. Additionally, Christopher Columbus famously used a lunar eclipse to his advantage in 1504, predicting the event to persuade indigenous people in Jamaica to provide him and his crew with supplies. 36. The moon has phases that are observable from Earth, with the full moon being the most recognizable. Each phase represents a different portion of the moon's surface illuminated by the sun as seen from Earth. These phases include new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, and waning crescent. This cycle of phases, known as the lunar month, plays a significant role in various calendars and cultural practices around the world. 37. The idea of mining the moon for resources has gained traction in recent years. The moon is rich in materials such as helium-3, a potential fuel for future nuclear fusion reactors, as well as rare earth elements, metals, and other valuable minerals. Mining these resources could support space exploration and development, providing materials for construction, fuel, and other needs. However, the technical and ethical challenges of lunar mining are significant, requiring careful consideration and international cooperation. 38. The moon has been a focus of international space missions beyond the Apollo program, with numerous countries contributing to lunar exploration. The Soviet Union's Lunar program achieved several firsts, including the first spacecraft to impact the moon and the first unmanned lunar landing. More recently, missions from countries like China, India, and the European Space Agency have expanded our understanding of the moon through orbital studies, landers, and rovers, highlighting the global interest in lunar science and exploration. 39. The moon's surface is dotted with volcanic domes, which are low, broad, rounded hills formed by the eruption of viscous lava. Unlike the large basaltic plains of the Mare, these domes are composed of thicker lava that piles up near the vent. Studying these volcanic features provides insights into the moon's volcanic activity and the composition of its interior, helping scientists piece together the history of lunar volcanism. 40. The lunar crust contains significant quantities of a mineral called anorthosite, which is primarily composed of plagioclase feldspar. This mineral gives the lunar highlands their bright appearance and is believed to have formed early in the moon's history as part of a global magma ocean that cooled and crystallized. The study of anorthosite-rich rocks brought back by the Apollo missions has provided valuable information about the moon's early differentiation and geological evolution. 41. The moon has a subtle but detectable gravitational anomaly called maskins, or mass concentrations. These are regions of higher gravitational pull caused by dense, buried structures beneath the lunar surface, such as ancient lava flows or impact basins filled with dense material. Maskins affect the orbits of spacecraft around the Moon, requiring careful navigation adjustments for lunar missions. Understanding these anomalies also helps scientists learn more about the Moon's interior structure and geological history. 42. The Moon has long been a source of speculation and inspiration for science fiction writers who have imagined a variety of futures involving lunar exploration and colonization. From H.G. Wells' The First Man in the Moon to Arthur C. Clarke's 2001, A Space Odyssey, the Moon has served as a setting for tales of adventure, discovery, and human ingenuity. These stories have not only entertained but also inspired real-world scientists and engineers to turn fiction into reality, driving humanity's quest to explore and understand our nearest celestial neighbor. 43. The Moon has played a pivotal role in advancing our understanding of the solar system's history. Lunar samples brought back by the Apollo missions have been extensively studied, revealing details about the age and composition of the Moon's crust. These samples indicate that the Moon formed around 4.5 billion years ago, shortly after the formation of the solar system, making it a valuable record of early planetary processes and the history of impacts in our solar neighborhood. 44. The Moon has a significant effect on Earth's axial tilt, stabilizing it over long periods. This stabilization has contributed to the relatively stable climate conditions that have allowed life to flourish on our planet. Without the Moon's gravitational influence, Earth's axial tilt could vary more dramatically, leading to extreme climate shifts and potentially making the planet less hospitable for life. 45. The Moon's distance from Earth varies due to its elliptical orbit, ranging from about 356,500 kilometers to 121,500 miles. At its closest perigee to about 406,700 kilometers to 152,700 miles at its farthest apogee. These variations influence the apparent size of the Moon in our sky, creating phenomena such as supermoons when the full moon occurs near perigee, appearing larger and brighter than usual. 46. Lunar dust, or regolith, poses significant challenges for exploration due to its abrasive nature and tendency to cling to surfaces. This find dust can damage equipment, infiltrate habitats, and pose health risks to astronauts if inhaled. Developing effective methods to mitigate lunar dust's impact is crucial for the safety and success of long-term missions and lunar habitation, making it a key area of research for future space exploration. 47. The concept of terraforming the Moon to make it more habitable for humans has been a topic of speculative discussion. While current technology and knowledge do not allow for large-scale environmental modifications, ideas such as creating enclosed habitats with controlled environments or using in-situ resources for construction and life support are being explored. These concepts highlight the creative thinking and innovation required to overcome the challenges of living on another celestial body. 48. The Moon's gravitational influence extends beyond just the tides, affecting Earth's geophysical processes. This includes slight variations in the Earth's rotation speed and wobble, known as precession and nutation. These subtle effects, though not immediately noticeable, are important in long-term climate modeling and understanding the dynamics of Earth's rotational behavior over millennia. 49. The exploration of the Moon has driven technological advancements in various fields, including robotics, materials science, and telecommunications. For example, the development of lunar rovers and landers has spurred innovations in autonomous navigation and remote operation, technologies that are now applied in other industries such as autonomous vehicles and remote surgery. These advancements illustrate how space exploration can lead to significant technological progress with broad applications. 50. The Moon has no magnetic field of its own, unlike Earth. However, the Moon's surface rocks retain a record of ancient magnetic fields, suggesting that the Moon once had a magnetic field generated by a dynamo effect in its core. Studying these magnetic properties provides insights into the moon's thermal and geological history, helping scientists understand how and why its magnetic field dissipated over time. 51. The moon's libration, a term for its slight oscillating motion, allows observers on Earth to see slightly more than half of its surface over time. This back-and-forth rocking motion is caused by the eccentricity of the moon's orbit and its axial tilt. Libration reveals about 59% of the moon's surface to observers on Earth, allowing glimpses of the edges of the far side that would otherwise be hidden. 52. The moon's lack of an atmosphere results in a sky that is perpetually black, even during lunar daytime. Without an atmosphere to scatter sunlight, as on Earth, the sky remains dark, offering a stark contrast to the brightly lit lunar surface. This means that stars are visible even when the sun is shining, providing a unique and striking visual experience for anyone on the moon. 53. The concept of lunar bases has evolved from science fiction to serious scientific and engineering proposals. Plans for establishing permanent or semi-permanent habitats on the moon include using lunar materials to build structures, leveraging local resources for water and oxygen, and developing sustainable energy sources such as solar power. These bases could serve as platforms for scientific research, resource extraction, and as stepping stones for further space exploration, including missions to Mars and beyond. 54. Lunar regolith, the layer of loose, fragmented rock and dust covering the moon's surface, holds clues to the history of solar system impacts. By studying the composition and distribution of regolith, scientists can reconstruct the timeline of major asteroid and comet impacts that have shaped the moon's surface over billions of years. This research provides insights into the broader history of impacts across the solar system. 55. The moon's surface exhibits features known as lunar swirls, which are bright, sinuous patterns often associated with magnetic anomalies. These swirls, such as Reiner Gamma and Reiner Gamma 2, stand out against the darker lunar background and are thought to be caused by interactions between the moon's surface and its magnetic field. The exact mechanism behind their formation remains an active area of research. 56. Lunar eclipses provide valuable opportunities for scientific observation and public engagement. Astronomers use lunar eclipses to study Earth's atmosphere by observing how sunlight filters through it, providing insights into atmospheric composition and dynamics. These events also captivate the public, offering a rare chance to witness a dramatic celestial event and prompting interest in astronomy and space science. 57. The moon's gravity influences the orbits of artificial satellites around Earth, including those in low Earth orbit (LEO). Variations in lunar gravity can cause subtle perturbations in satellite trajectories, requiring periodic adjustments to maintain their intended orbits. Understanding these gravitational interactions is essential for satellite operations and space situational awareness. 58. The moon is a potential site for future astronomical observatories and telescopes. Because of its lack of atmosphere and minimal light pollution, the lunar surface offers a stable and unobstructed platform for observing the universe across a wide range of wavelengths. Concepts for lunar observatories include radio telescopes on the far side, where they can shield it from Earth's radio interference. 59. Lunar volcanism played a significant role in shaping the moon's surface billions of years ago. Evidence from volcanic deposits, such as lava flows and volcanic domes, indicates that the moon experienced periods of intense volcanic activity early in its history. Studying these volcanic features provides insights into the moon's thermal evolution, internal dynamics, and the processes that shaped its geology over time. 60. The moon has been visited by robotic spacecraft from several countries besides the United States and the Soviet Union. For example, the Chinese Change program has successfully landed multiple spacecraft on the lunar surface, including the Change 4 mission, which made the first soft landing on the far side of the moon in January 2019. These missions continue to expand our understanding of the Moon's geology, resources, and potential for future exploration. 61. The Moon's surface is constantly bombarded by micrometeoroids and larger meteoroids, which create impact craters and contribute to the lunar regolith. These impacts occur at velocities exceeding 17 kilometers per second, about 38,000 miles per hour, resulting in explosive collisions that eject debris across the lunar surface. Studying impact craters provides valuable information about the frequency and nature of impacts in the inner solar system. 62. The Moon's orbit around Earth is not perfectly stable due to gravitational interactions with the Sun and other planets. Over time, these gravitational perturbations cause variations in the Moon's orbital parameters, including its eccentricity and inclination. Understanding these orbital dynamics is crucial for accurately predicting lunar positions and planning future space missions. 63. Lunar exploration has led to the discovery of significant resources on the Moon, including water ice and permanently shadowed craters at the poles. This water ice could be extracted and processed into drinking water, breathable oxygen, and hydrogen for rocket fuel. Accessing these resources locally would reduce the cost and complexity of lunar missions and enable sustainable human presence on the Moon. 64. The Moon experiences phenomena known as moonquakes, which are seismic tremors similar to earthquakes on Earth. These moonquakes can be caused by a variety of factors, including tidal stresses, meteoroid impacts, and the gradual cooling and contraction of the Moon's interior. Studying moonquakes provides insights into the Moon's internal structure and the ongoing processes that shape its geology. 65. The Moon's gravitational influence affects Earth's climate on long time scales through variations in orbital parameters known as Milankovitch cycles. These cycles, including changes in the tilt and eccentricity of Earth's orbit, influence the distribution of solar radiation received by our planet. These variations are linked to changes in Earth's climate over tens of thousands to hundreds of thousands of years, impacting global temperature patterns and the onset of ice ages. 66. The Moon's surface reflects sunlight differently depending on its location and composition. Lunar highlands, composed primarily of anorthosite rock, appear brighter than the darker basaltic Mare. This variation in reflectivity, or albedo, affects the Moon's overall appearance and visibility from Earth. 67. Lunar reconnaissance missions have identified regions of the Moon with elevated concentrations of rare earth elements, Res, and other valuable minerals. These resources could potentially support future lunar mining operations, providing materials for advanced technologies and space exploration infrastructure. 68. The Moon's rotational axis is tilted by about 1.5 degrees relative to its orbit around Earth. This small axial tilt contributes to subtle variations in lighting and shadows across the lunar surface, influencing the visibility of surface features and enhancing the aesthetic appeal of lunar photography. 69. Lunar exploration has revealed evidence of ancient lava tubes beneath the Moon's surface. These underground tunnels, formed by lava flows billions of years ago, could provide natural shelters for future human habitats, shielding residents from radiation, micrometeoroids, and extreme temperature fluctuations. 70. The Moon's thin exosphere contains trace amounts of various gases, including helium, neon, hydrogen, and argon. These gases are believed to originate from solar wind interactions with the lunar surface and the release of volatiles from lunar rocks and regolith. 71. The Moon's far side, often incorrectly referred to as the dark side, has a different geological composition compared to the near side. It is dominated by highlands and lacks large, dark Mare basins which are abundant on the near side. The geological differences between the two hemispheres provide valuable insights into the Moon's formation and evolution. 72. The Moon has been instrumental in testing fundamental principles of physics, including theories of gravitation and relativity. Experiments such as the Lunar Laser Ranging Experiment (LLR) have used reflected laser beams to precisely measure the distance between Earth and the Moon. These measurements have confirmed predictions of Einstein's theory of general relativity and provided insights into the dynamics of Earth-Moon interactions. 73. The Moon's gravitational pull influences Earth's axial tilt and axial precession, affecting the planet's climate and seasons over long time scales. These variations contribute to Milankovitch cycles, which are linked to periods of glaciation and climate change throughout Earth's history. Understanding these cycles helps scientists reconstruct past climates and predict future environmental changes. 74. The Moon has significant cultural and religious symbolism across different civilizations. In many cultures, the lunar cycle has been associated with fertility, agriculture, and the passage of time. Lunar phases have also influenced religious calendars and rituals, such as determining the dates of festivals and holidays based on the appearance of the full moon. 75. The Moon's gravitational interaction with Earth creates a tidal bulge not only in the oceans but also in Earth's crust and mantle. This tidal deformation causes small but measurable variations in Earth's surface elevation and can influence seismic activity, particularly in regions with high tidal ranges. 76. Lunar exploration has revealed evidence of volcanic activity on the Moon's surface, including volcanic domes and lava flows. These volcanic features provide clues about the Moon's thermal history and the processes that shaped its geology billions of years ago. Studying lunar volcanism also informs our understanding of volcanic activity on other rocky bodies in the solar system. 77. The Moon's lack of atmosphere allows for long-term preservation of surface features, including impact craters and ancient geological formations. These well-preserved records provide valuable insights into the history of the solar system, offering clues about the frequency of asteroid and comet impacts and the evolution of planetary surfaces over billions of years. 78. The Moon's surface temperature varies significantly between lunar day and night due to its lack of atmosphere. During the lunar day, temperatures can reach highs of about 127 degrees Celsius to 161 degrees Fahrenheit near the equator, while at night, temperatures plummet to lows of approximately minus 173 degrees Celsius minus 180 degrees Fahrenheit. These extreme temperature swings pose challenges for lunar exploration and habitat design, requiring innovative thermal control systems to protect equipment and astronauts. 79. The Moon's gravitational field is uneven and varies across its surface, influenced by variations in crustal thickness and density. These gravitational anomalies, known as Maskin's mass concentrations, affect spacecraft orbits and lunar missions. Understanding Maskins is essential for precise navigation and planning safe landing sites on the Moon. 80. Lunar samples brought back by the Apollo missions have provided valuable insights into the Moon's geological history and early solar system processes. Analysis of lunar rocks and regolith has revealed isotopic signatures that differ from those on Earth, suggesting distinct origins and evolutionary pathways for the Moon and our planet. 81. The Moon's orbit is not perfectly circular but rather elliptical, with an eccentricity of about 0.054. This orbital eccentricity causes variations in the Moon's distance from Earth, ranging from approximately 363,300 kilometers to 125,600 miles. At apogee to 405,500 kilometers to 151,900 miles at perigee. These variations influence tidal forces and the apparent size of the Moon in the sky. 82. The Moon's surface is constantly bombarded by cosmic rays and solar radiation, which pose health risks to astronauts and affect the longevity of equipment on the lunar surface. Shielding against radiation is a critical consideration for future lunar missions and habitats, requiring advanced materials and design strategies to ensure astronaut safety and mission success. 83. The moon's influence on Earth extends beyond tides and climate. Some studies suggest that the moon may have played a role in the origin and evolution of life on Earth by stabilizing its axial tilt and climate over geological timescales. This stable environment provided by the moon's gravitational interaction with Earth may have facilitated the development and persistence of life on our planet. 84. The moon has a phenomenon called lunar swirls, which are bright, sinuous features often associated with magnetic anomalies. These swirls, such as Reiner Gamma and Reiner Beta, stand out against the darker lunar background and are thought to result from interactions between the moon's surface and its magnetic field. The exact mechanisms behind their formation are still under study, but they provide intriguing insights into the moon's magnetic history and surface processes. 85. The moon's crust is thinner on the near side compared to the far side, with the average thickness ranging from about 30 kilometers (18.6 miles) to 60 kilometers (37.3 miles). This asymmetry in crustal thickness is believed to be due to differences in geological processes and the distribution of impact basins between the two hemispheres. Studying these variations helps scientists understand the moon's geological evolution and internal structure. 86. The moon has regions known as lobate scarps, which are thrust faults that formed as the lunar crust contracted and wrinkled over time. These scarps, such as the Dorsa Geikie and the Taurus Littrow fault, are visible in high-resolution images and have provided valuable clues about the moon's ongoing geological activity and the forces shaping its surface. 87. The moon's surface contains glass beads called agglutinates, which form from the intense heat and pressure generated during meteorite impacts. These tiny glass particles are found in lunar soil and rock samples and provide evidence of the moon's violent history of bombardment by micrometeoroids and larger impactors. Studying agglutinates helps scientists reconstruct the frequency and intensity of impacts on the moon over billions of years. 88. The moon's South Pole region has large permanently shadowed craters, some of which are believed to contain water ice and other volatiles. These cold traps preserve materials that have accumulated over billions of years, offering a glimpse into the volatile-rich history of the moon and potentially providing valuable resources for future lunar missions and human exploration. 89. The moon's magnetic field is significantly weaker than Earth's, but it does exhibit localized magnetic anomalies in certain regions. These anomalies are thought to be remnants of past magnetic activity when the moon had a more substantial magnetosphere, possibly generated by a dynamo effect in its molten core. Understanding these magnetic anomalies helps scientists unravel the moon's geological history and internal dynamics. 90. The moon experiences thermal moonquakes, which are caused by the expansion and contraction of the lunar crust due to the extreme temperature changes between lunar day and night. These moonquakes differ from the more traditional tectonic earthquakes seen on Earth, which are primarily driven by plate tectonics. Studying these moonquakes provides valuable insights into the moon's thermal properties and internal structure. 91. The moon's surface is covered with impact craters of various sizes, ranging from small, bowl-shaped craters to large, multi-ring basins like the South Politkin Basin. These craters are formed by the impact of asteroids, comets, and meteoroids over billions of years and provide a record of the solar system's history of impacts. Some craters have remained relatively pristine due to the moon's lack of atmosphere and geological activity. 92. The moon's rotation is tidally locked to Earth, meaning it rotates on its axis in the same amount of time it takes to orbit Earth, approximately 27.3 days. As a result, the same side of the moon always faces Earth, with the far side remaining hidden from view until space exploration missions provided the first images in the mid-20th century. 93. The moon's composition is predominantly made up of rocky materials, with silicate minerals like plagioclase, pyroxene, and olivine being common. These minerals crystallized from a global magma ocean early in the Moon's history and make up the lunar crust and mantle. The study of lunar samples brought back by Apollo missions and lunar meteorites provides valuable information about the Moon's chemical and mineralogical makeup. 94. The Moon has been observed to have transient phenomena called lunar transient phenomena (LTP), which include brief flashes of light, color changes, and obscuration events on its surface. These phenomena are often attributed to meteoroid impacts, gas releases, or electrostatic discharges, but their exact nature and cause remain a subject of scientific investigation and debate. 95. The Moon's surface is covered with regolith, a layer of fragmented rock and soil created by the continuous bombardment of meteoroids and micrometeoroids. Lunar regolith ranges in depth from a few meters on the Mare to tens of meters in the Highlands and serves as a record of the Moon's geological history and the effects of space weathering processes over billions of years. 96. The Moon exhibits a phenomenon known as lunar libration, which causes slight oscillations in its orientation as seen from Earth. Libration results from variations in the Moon's orbital speed and axial tilt, allowing observers to see slightly more than 59% of its surface over time. This motion provides views of lunar features near the edges of the apparent disk that would otherwise be hidden from Earth. 97. The Moon has been observed to have transient lunar phenomena (TLP), which are short-lived changes observed on its surface, such as bright flashes, color variations, or haze-like appearances. These phenomena, reported since the 18th century, remain poorly understood and are subjects of ongoing scientific investigation. Possible explanations include outgassing events, meteoroid impacts, or electrostatic effects. 98. The Moon's surface is highly reflective in radar wavelengths, making it visible to radar instruments on Earth and spacecraft. Radar mapping missions, such as those conducted by NASA's Lunar Reconnaissance Orbiter (LRO), have provided detailed topographic maps and insights into the Moon's subsurface structure, including buried impact craters and volcanic features. 99. The Moon's gravitational influence creates a phenomenon known as earthshine, where sunlight reflected from Earth illuminates the dark portion of the Moon's surface during its crescent phase. This faint glow of earthshine provides indirect evidence of the Earth's albedo, or reflectivity, and has been observed and studied by astronomers for centuries. 100. The Moon has been proposed as a potential site for future astronomical observatories and radio telescopes due to its stable surface and lack of atmospheric interference. Concepts for lunar observatories include placing telescopes on the far side of the Moon, shielded from Earth's radio frequency interference and offering a clear view of the universe across various wavelengths. 101. The Moon's magnetic field is globally weak but locally varies due to remnants of past magnetic activity in its crust. These localized magnetic anomalies, known as maskins, affect the orbits of spacecraft around the Moon and have implications for future lunar exploration missions. Studying maskins provides insights into the Moon's geological history and internal structure. 102. The Moon's surface is composed of distinct geological features, including rilles, which are long, narrow depressions or valleys. Rilles can be categorized into two main types: sinuous rilles, believed to be ancient lava channels formed by volcanic activity, and straight rilles, which are linear features likely created by faulting or collapse processes. Studying these rilles provides insights into the Moon's volcanic and tectonic history. 103. The Moon has regions of lunar swirls, which are unique bright features often associated with localized magnetic anomalies. These swirls, such as Reiner Gamma and Reiner Beta, stand out against the darker lunar background and are believed to result from interactions between the Moon's surface and its magnetic field. Understanding the formation of lunar swirls helps scientists unravel the complex interactions between solar wind, magnetic fields, and surface materials on airless bodies. 104. The Moon's impact craters vary in size and morphology, ranging from simple bowl-shaped depressions to complex multi-ring basins like the Oriental Basin. These basins are some of the largest and most well-preserved impact structures in the solar system, providing a record of the intense bombardment that shaped the Moon's surface during its early history. Studying impact craters helps scientists understand the frequency and effects of impacts across the solar system. 105. The Moon's surface is characterized by regolith, a layer of loose, fragmented rock and soil covering solid bedrock. Lunar regolith is created by the continuous bombardment of micrometeoroids and larger impactors, which pulverize and mix surface materials over billions of years. Regolith serves as a record of the Moon's geological history and plays a crucial role in understanding space weathering processes and the composition of planetary surfaces. 106. The Moon's lack of atmosphere allows for the preservation of ancient impact craters and geological features that would be eroded or modified on Earth. These well-preserved features provide valuable insights into the early history of the solar system and the processes that shaped planetary bodies billions of years ago. Studying lunar geology helps scientists unravel the mysteries of planetary formation and evolution. 107. The Moon's far side, often incorrectly referred to as the dark side, has a different geological composition compared to the near side. It is dominated by rugged highlands and lacks the large, dark Mare basins that are abundant on the near side. The geological differences between the two hemispheres provide valuable insights into the Moon's formation and evolution, offering clues about early differentiation processes and the distribution of impact basins. 108. The Moon exhibits a phenomenon known as thermal segregation, where different types of lunar soil particles sort themselves out based on size and composition due to their ability to absorb and retain heat differently. This segregation process affects the thermal properties of the lunar regolith and plays a role in shaping the temperature gradients across the lunar surface. 109. The Moon's lunar swirls, such as those observed at Reiner Gamma and Reiner Beta, are thought to result from interactions between the Moon's surface and its magnetic field. These bright, sinuous features stand out against the darker lunar background and are believed to be caused by magnetic anomalies affecting the distribution and movement of surface materials. 110. The Moon's impact basins, such as the South Politkin Basin, are some of the largest and deepest craters in the solar system. These basins formed billions of years ago from the impacts of large asteroids or comets and are characterized by multiple rings of mountainous peaks and fractured terrain. Studying these basins provides insights into the early history of the Moon and the dynamics of impact events in the early solar system. 111. The Moon's volcanic plains, known as Mare, are large, dark areas on the lunar surface formed by ancient lava flows. These basaltic plains cover about 16% of the Moon's surface and are believed to have formed from volcanic activity between 3 and 4 billion years ago. The study of lunar Mare provides valuable information about the Moon's thermal evolution and volcanic history. 112. The Moon's gravity is about 1/6 that of Earth's, which affects the movement of objects and the behavior of fluids on its surface. This low gravity has implications for future lunar exploration, including the design of spacecraft, habitats, and equipment to operate effectively in a reduced gravity environment. 113. The Moon has no significant atmosphere, which means it lacks weather phenomena such as clouds, winds, and rain. This airless environment allows for clear views of the lunar surface from Earth and provides an ideal location for astronomical observations across various wavelengths of light. 114. The Moon's peak rings are unique geological features found in some of its largest impact basins, including the Oriental Basin. These rings are formed by rebounding material that collapses inward after a large impact, creating concentric rings of mountains and valleys. Studying peak rings provides insights into the dynamics of high-energy impacts and the processes that shape planetary surfaces. 115. The moon's lunar swirls, such as those at Mare Ingenii and Mare marginis, exhibit complex interactions between surface materials, magnetic fields, and solar wind. These bright features stand out against the darker lunar background and are believed to be associated with localized magnetic anomalies. Understanding the formation and evolution of lunar swirls helps scientists investigate the moon's magnetic history and surface processes. 116. The moon's lobate scarps are geological features that formed as the lunar crust contracted and wrinkled over time. These thrust faults, such as those in the Taurus-Litra Valley, provide evidence of ongoing geological activity and the forces shaping the moon's surface. Studying lobate scarps helps scientists understand the moon's internal dynamics and the processes responsible for crustal deformation. 117. The moon's mascons mass concentrations are localized gravitational anomalies that affect spacecraft orbits around the moon. These anomalies, such as those in the Mare Serenitatis and Mare Smythii regions, are caused by variations in the density of underlying crustal materials. Understanding mascons is crucial for precise navigation and landing operations during lunar missions. 118. The moon's lunar regolith contains a mixture of fine dust, rocky debris, and fragmented bedrock that covers its surface to depths ranging from a few meters to tens of meters. This regolith is created by the continuous bombardment of meteoroids and micrometeoroids over billions of years and serves as a record of the moon's geological history. Studying lunar regolith provides insights into space weathering processes, the distribution of impact craters, and the composition of planetary surfaces. 119. The moon's riles are long, winding valleys that snake across its surface, such as those in the Valles Reiter region. These features are believed to have formed through a combination of volcanic activity, collapse processes, and tectonic forces. Studying lunar riles helps scientists understand the geological processes that shaped the moon's surface and its evolution over time. 120. The moon's mascons mass concentrations are dense regions beneath its surface that have a stronger gravitational pull than surrounding areas. These anomalies, such as those in the Imbrium, Serenitatis, and Chrysium basins, were discovered during lunar orbiting missions and affect the orbits of spacecraft around the moon. Understanding mascons is crucial for precise navigation and planning future lunar missions. 121. The moon's lunar swirls, such as those at Mare Ingenii and Mare marginis, are enigmatic bright features characterized by high albedo and complex morphology. These swirls are believed to result from interactions between the moon's surface and its magnetic field, which may influence the distribution and movement of surface materials. Studying lunar swirls provides insights into the moon's magnetic history and surface processes. 122. The moon's lunar highlands are rugged, heavily cratered terrains predominantly composed of anorthosite, a type of rock-rich and plagioclase feldspar. These highlands cover much of the moon's near side and represent the oldest crustal material dating back over 4 billion years. The study of lunar highlands provides valuable information about the early history of the moon, including its formation and differentiation processes. 123. The moon's volcanic domes are small, steep-sided mounds formed from the eruption of viscous lava flows onto the lunar surface. These domes, such as those in the Marius Hills region, provide evidence of past volcanic activity on the moon and insights into its geological evolution. Studying volcanic domes helps scientists understand the composition of lunar magma and the processes that shaped volcanic landscapes. 124. The moon's lunar maria are large, dark plains on its surface formed by ancient basaltic lava flows. These volcanic plains, such as those in the Oceanus Procellarum and Mare Imbrium regions, cover about 16% of the moon's surface and are significantly younger than the surrounding highlands. The study of lunar maria provides insights into the moon's thermal history, volcanic activity, and the interactions between magma and regolith. 125. The Moon's ray systems are radial patterns of bright ejecta material that extend outward from large impact craters. These rays, such as those associated with the Tycho and Copernicus craters, are composed of fine-grained material ejected during impact events and can extend for hundreds of kilometers across the lunar surface. Studying ray systems helps scientists understand the dynamics of impact processes and the distribution of material ejected during high-energy collisions. 126. The Moon's lunar swirls, like those at Mare Ingenii and Mare Marginis, exhibit unique reflectivity patterns that defy simple explanations. These bright features, possibly linked to magnetic anomalies, remain a topic of ongoing research, with hypotheses ranging from magnetic shielding of regolith to electrostatic processes influencing surface dust distribution. 127. The Moon's impact basins, such as the Oriental Basin, feature complex structures including central peaks and concentric rings formed by massive impacts. These basins provide valuable insights into early solar system dynamics, impact processes, and the Moon's geologic evolution over billions of years. 128. The Moon's volcanic cones, found in regions like the Marius Hills, are small, conical landforms formed by eruptions of viscous lava. These features suggest that volcanic activity on the Moon persisted for extended periods, contributing to the modification of its surface and revealing clues about the composition and behavior of lunar magma. 129. The Moon's lobate scarps, such as those near the Apollo 17 landing site, are thrust faults created as the Moon's crust contracted over time. These features provide evidence of ongoing tectonic activity and crustal deformation, offering insights into the Moon's thermal evolution and internal dynamics. 130. The Moon's lunar riles, such as those in the Valles Sirteri region, are sinuous valleys believed to result from a combination of volcanic activity and collapse processes. Studying lunar riles helps scientists understand the history of lava channel formation and the role of volcanic processes in shaping the Moon's surface morphology. 131. The Moon's regolith breccias are rocks composed of fragmented materials compacted together by impacts and other geological processes. These breccias, found in lunar samples returned by Apollo missions, provide a record of multiple impact events and offer insights into the history of meteoroid bombardment on the Moon's surface. 132. The Moon's lunar swirls, such as those at Mare Ingenii and Reiner Gamma, are bright, sinuous features often associated with magnetic anomalies. These swirls stand out against the darker lunar background and are believed to result from interactions between the Moon's surface materials and its weak magnetic field remnants. Studying these swirls helps scientists understand the complex interactions between solar wind, magnetic fields, and surface materials on airless bodies. 133. The Moon's lobate scarps, such as those near the Apollo 17 landing site, are steep cliffs that formed as the lunar crust contracted and thrust upward. These thrust faults provide evidence of ongoing tectonic activity and crustal deformation on the Moon, offering insights into its thermal evolution and internal dynamics. 134. The Moon's lunar highlands are rugged, heavily cratered terrains predominantly composed of anorthosite, a type of rock rich in plagioclase feldspar. These highlands cover much of the Moon's near side and represent some of the oldest crustal material in the solar system, dating back over 4 billion years. The study of lunar highlands provides valuable information about the early history of the Moon, including its formation and differentiation processes. 135. The Moon's riles, such as those in the Valles Sirteri region, are long, winding valleys believed to have formed through a combination of volcanic activity and collapse processes. These features provide insights into the history of lunar volcanic activity and the behavior of lava flows on airless bodies like the Moon. 136. The Moon's lunar maria, such as those in the Oceanus Procellarum and Mare Imbrium regions, are large, dark plains formed by ancient basaltic lava flows. These volcanic plains cover about 16% of the Moon's surface and are significantly younger than the surrounding highlands. Studying Lunar Maria provides insights into the Moon's thermal history, volcanic activity, and the interactions between magma and Regolith 137. The Moon's mascons mass concentrations are dense regions beneath its surface that have a stronger gravitational pull than surrounding areas. These anomalies, such as those in the Mare Serenitatis and Chrysium regions, were discovered during lunar orbiting missions and affect the orbits of spacecraft around the Moon. Understanding mascons is crucial for precise navigation and planning future lunar exploration missions. 138. The Moon's lunar exosphere is a thin layer of gases and particles that extends several hundred kilometers above its surface. This exosphere consists mainly of helium, neon, hydrogen, and argon released from the lunar surface due to solar wind bombardment and radioactive decay of elements within lunar rocks. Studying the lunar exosphere provides insights into the volatile transport processes and interactions between the Moon and its surrounding space environment. 139. The Moon's lunar swirls, such as those at Mare Ingenii and Reiner Gamma, exhibit unusual optical properties, including high reflectivity and distinct color variations. These features are hypothesized to result from interactions between the Moon's surface materials, magnetic fields, and micrometeoroid bombardment. Understanding the formation and evolution of lunar swirls helps scientists investigate the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies. 140. The Moon's impact melt breccias are rocks formed from the mixture of melted and resolidified materials during large impact events. These breccias, found in impact craters like Tycho and Copernicus, provide valuable clues about the intense thermal and shock processes that shaped the lunar surface. Studying impact melt breccias helps scientists reconstruct the dynamics of ancient impact events and their effects on planetary bodies. 141. The Moon's lunar transient phenomena LTP are brief, localized changes observed on its surface, such as flashes of light, color variations, or hazes. These phenomena, reported by astronomers since the 18th century, remain poorly understood and are subjects of ongoing scientific investigation. Possible explanations include meteoroid impacts, outgassing events, or electrostatic processes affecting surface dust. 142. The Moon's ray systems, such as those associated with the Tycho and Copernicus craters, are radial patterns of bright ejecta material extending hundreds of kilometers across the lunar surface. These rays consist of fine-grained debris ejected during impact events and provide valuable insights into the dynamics of high-energy collisions and the distribution of impact material on planetary surfaces. 143. The Moon's lunar swirls, such as those at Mare Ingenii and Reiner Gamma, are believed to be related to localized magnetic anomalies affecting surface materials. These bright features exhibit distinct albedo patterns and are thought to result from interactions between the Moon's surface and its weak magnetic field remnants. Studying lunar swirls provides insights into the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies like the Moon. 144. The Moon's lunar regolith contains a wide range of particle sizes, from fine dust to larger rocks and boulders, created by the continuous bombardment of micrometeoroids and larger impactors. This layer of fragmented material covers the solid bedrock and can reach depths of several meters on the lunar surface. Studying lunar regolith provides insights into space weathering processes, the history of impact events, and the composition of planetary surfaces. 145. The Moon's lunar swirls, such as those at Mare Ingenii and Reiner Gamma, are characterized by their bright, sinuous features that stand out against the darker lunar background. These swirls are believed to result from interactions between the Moon's surface materials and its weak magnetic field remnants. Understanding the formation and evolution of lunar swirls helps scientists investigate the complex interactions between solar wind, magnetic fields, and surface materials on airless bodies. 146. The moon's rilles, such as those in the Valles Tertiary region, are sinuous valleys that wind across its surface believed to have formed through a combination of volcanic activity and collapse processes. These features provide insights into the history of lunar volcanic activity and the behavior of lava flows on airless bodies like the Moon. 147. The Moon's impact basins, such as the South Polytkin Basin, are some of the largest and deepest craters in the solar system, formed by massive impacts billions of years ago. These basins exhibit complex structures, including central peaks, multiple rings, and fractured terrains, providing valuable insights into the dynamics of impact processes and the geological evolution of planetary bodies. 148. The Moon's lunar highlands are rugged, heavily cratered terrains composed of anorthosite, a type of rock rich in plagioclase feldspar. These highlands cover much of the Moon's near side and represent some of the oldest crustal material in the solar system, dating back over 4 billion years. The study of lunar highlands provides valuable information about the early history of the Moon, including its formation and differentiation processes. 149. The Moon's lunar volcanoes, such as those in the Mare Hills region, are small, conical landforms formed by the eruption of viscous lava flows onto the lunar surface. These volcanic features suggest that lunar volcanic activity persisted for extended periods, contributing to the modification of its surface and revealing clues about the composition and behavior of lunar magma. 150. The Moon's lunar dust is composed of fine particles less than 1 millimeter in size, created by the continuous bombardment of meteoroids and micrometeoroids on its surface. This dust is electrostatically charged and can cling to surfaces, posing challenges for lunar exploration and potentially affecting equipment and astronaut suits. 151. The Moon's lunar swirls, such as those at Mare, Ingenii, and Reiner Gamma, exhibit unique optical properties characterized by high reflectivity and distinct color contrasts. These features are hypothesized to result from interactions between the Moon's surface materials, magnetic fields, and micrometeoroid bombardment. Understanding the formation and evolution of lunar swirls helps scientists investigate the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies. 152. The Moon's lunar transient phenomena (LTP) are brief, localized changes observed on its surface, such as flashes of light, color variations, or hazes. These phenomena, reported by astronomers since the 18th century, remain poorly understood and are subjects of ongoing scientific investigation. Possible explanations include meteoroid impacts, outgassing events, or electrostatic processes affecting surface dust. 153. The Moon's lobate scarps, such as those near the Apollo 17 landing site, are steep cliffs formed as the lunar crust contracted and thrust upward. These thrust faults provide evidence of ongoing tectonic activity and crustal deformation on the Moon, offering insights into its thermal evolution and internal dynamics. 154. The Moon's impact melt breccias are rocks formed from the mixture of melted and resolidified materials during large impact events. These breccias, found in impact craters like Tycho and Copernicus, provide valuable clues about the intense thermal and shock processes that shaped the lunar surface. Studying impact melt breccias helps scientists reconstruct the dynamics of ancient impact events and their effects on planetary bodies. 155. The Moon's lunar regolith, composed of fragmented rock and soil, plays a crucial role in space weathering processes and the distribution of volatile elements. This layer covers the lunar surface to depths ranging from a few meters to tens of meters and serves as a record of the Moon's geological history, including the frequency and intensity of impact events over billions of years. 156. The Moon's lunar swirls, such as those at Mare, Ingenii, and Reiner Gamma, exhibit peculiar brightness patterns and are often associated with localized magnetic anomalies. These features stand out against the darker lunar background and are hypothesized to result from interactions between the Moon's surface materials, magnetic fields, and micrometeoroid bombardment. Studying lunar swirls helps scientists investigate the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies. 157. The Moon's lunar highlands are regions predominantly composed of anorthosite, a type of rock rich in plagioclase feldspar. These rugged terrains cover much of the Moon's near side and represent some of the oldest crustal material in the solar system, dating back over 4 billion years. The study of lunar highlands provides valuable insights into the early history of the Moon, including its formation and differentiation processes. 158. The Moon's lunar volcanism is evidenced by the presence of volcanic features such as lava channels, domes, and volcanic cones in regions like the Mare Hills. These features suggest that lunar volcanic activity persisted for extended periods, contributing to the modification of its surface and providing clues about the composition and behavior of lunar magma. 159. The Moon's lunar regolith, consisting of fragmented rock and soil, varies in composition and texture across different regions of its surface. This layer is created by the continuous bombardment of meteoroids and micrometeoroids and plays a critical role in space weathering processes, the distribution of volatile elements, and understanding the geological history of the Moon. 160. The Moon's lunar transient phenomena (LTP) are transient changes observed on its surface, such as flashes of light, color variations, or hazes. These phenomena, reported by astronomers since the 18th century, remain poorly understood and are subjects of ongoing scientific investigation. Possible explanations include meteoroid impacts, outgassing events, or electrostatic processes affecting surface dust. 161. The Moon's mascons mass concentrations are dense regions beneath its surface that create local gravitational anomalies affecting spacecraft orbits. These anomalies, such as those in the Mare Serenitatis and Crisium regions, were discovered during lunar orbiting missions and are crucial for precise navigation and planning future lunar exploration missions. 162. The Moon's lunar dust poses unique challenges for lunar exploration due to its fine, abrasive nature and electrostatic properties. This dust can adhere to surfaces, penetrate seals, and potentially cause mechanical issues with equipment and astronaut suits. Understanding lunar dust properties is essential for mitigating risks during prolonged lunar missions. 163. The Moon's lunar swirls, such as those at Mare, Ingenii, and Reiner Gamma, exhibit complex patterns of brightness and color variations that are not fully understood. These features are hypothesized to result from interactions between the Moon's surface materials, magnetic fields, and micrometeoroid bombardment. Investigating lunar swirls helps unravel the effects of magnetic shielding and surface weathering processes on airless bodies. 164. The Moon's impact melt rocks are formed from the intense heat and pressure generated during large impact events. These rocks, found in and around impact craters like Tycho and Copernicus, provide crucial insights into the thermal and shock processes that shaped the lunar surface. Studying impact melt rocks helps reconstruct the dynamics of ancient impact events and their effects on planetary bodies. 165. The Moon's lobate scarps, such as those near the Apollo 17 landing site, are geological features formed by thrust faulting as the lunar crust contracted and cooled. These scarps provide evidence of ongoing tectonic activity and crustal deformation on the Moon, offering insights into its thermal evolution and internal structure. 166. The Moon's lunar regolith, composed of fragmented rock and soil, holds a record of the solar system's history through the accumulation of impact ejecta over billions of years. This layer plays a vital role in space weathering processes, volatile transport, and the distribution of elements on planetary surfaces. 167. The Moon's ray systems, such as those associated with the Tycho and Copernicus craters, are radial patterns of bright ejecta material extending hundreds of kilometers across the lunar surface. These rays consist of fine-grained debris ejected during impact events and provide valuable insights into the dynamics of high-energy collisions and the distribution of impact material on planetary bodies. 168. The Moon's lunar swirls, such as those at Mare, Ingenii, and Reiner Gamma, exhibit distinct patterns of reflectivity and coloration that are not fully understood. These bright features are hypothesized to result from interactions between the Moon's surface materials, magnetic fields, and solar wind. Investigating lunar swirls helps scientists unravel the complex processes of magnetic shielding, surface weathering, and space weathering on airless bodies like the Moon. 169. The Moon's impact basins, such as the Imbrium Basin, exhibit complex structures including central peaks, multiple rings, and extensive ejecta blankets. These basins were formed by colossal impacts billions of years ago and provide valuable insights into the early history of the Moon and the dynamics of impact processes in the solar system. 170. The Moon's lunar highlands are rugged terrains dominated by ancient crustal material composed mainly of anorthosite, a type of rock rich in plagioclase feldspar. These highlands cover much of the Moon's near side and represent some of the oldest geological formations in the solar system, offering clues about the Moon's early formation and differentiation processes. 171. The Moon's lunar exosphere is a tenuous layer of gases and dust particles extending several hundred kilometers above its surface. This exosphere consists mainly of helium, neon, hydrogen, and argon released from the lunar surface due to solar wind bombardment and radioactive decay of elements within lunar rocks. Studying the lunar exosphere provides insights into the volatile transport processes and interactions between the Moon and its surrounding space environment. 172. The Moon's lunar volcanic domes, such as those in the Marius Hills region, are small, steep-sided mounds formed from the eruption of viscous lava flows onto the lunar surface. These domes suggest that volcanic activity on the Moon persisted for extended periods, contributing to the modification of its surface and revealing clues about the composition and behavior of lunar magma. 173. The Moon's lunar regolith, consisting of fragmented rock and soil, plays a crucial role in space weathering processes, impact dynamics, and the distribution of volatile elements. This layer covers the lunar surface to depths ranging from a few meters to tens of meters and provides a record of the Moon's geological history, including the frequency and intensity of impact events over billions of years. 174. The Moon's lunar swirls, such as those at Mare, Ingenii, and Reiner Gamma, exhibit unique optical properties characterized by high reflectivity and distinct color contrasts. These features are believed to result from interactions between the Moon's surface materials, magnetic fields, and micrometeoroid bombardment. Studying lunar swirls helps scientists understand the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies like the Moon. 175. The Moon's maskin's mass concentrations are dense regions beneath its surface that create local gravitational anomalies affecting spacecraft orbits. These anomalies, such as those in the Mare Serenitatis and Mare Smythii regions, were discovered during lunar orbiting missions and are crucial for precise navigation and planning future lunar exploration missions. 176. The Moon's lunar highlands, composed predominantly of anorthosite, cover much of its near side and represent some of the oldest crustal material in the solar system, dating back over 4 billion years. These rugged terrains provide valuable insights into the early history of the Moon, including its formation and differentiation processes. 177. The Moon's lunar regolith, consisting of fragmented rock and soil, varies in thickness and composition across different regions of its surface. This layer is created by the continuous bombardment of meteoroids and micrometeoroids and plays a critical role in space weathering processes, volatile transport, and understanding the geological history of the Moon. 178. The Moon's lunar transient phenomena LTP are brief, localized changes observed on its surface, such as flashes of light, color variations, or hazes. These phenomena, reported by astronomers since the 18th century, remain poorly understood and are subjects of ongoing scientific investigation. Possible explanations include meteoroid impacts, outgassing events, or electrostatic processes affecting surface dust. 179. The Moon's impact melt rocks are formed from the intense heat and pressure generated during large impact events. These rocks, found in and around impact craters like Tycho and Copernicus, provide crucial insights into the thermal and shock processes that shaped the lunar surface. Studying impact melt rocks helps reconstruct the dynamics of ancient impact events and their effects on planetary bodies. 180. The Moon's lunar swirls, such as those at Mare, Ingenii, and Reiner Gamma, are characterized by their high albedo and distinct patterns that defy simple explanations. These features are hypothesized to result from interactions between the Moon's surface materials, magnetic anomalies, and micrometeoroid bombardment. Understanding lunar swirls helps scientists unravel the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies like the Moon. 181. The Moon's lunar highlands, predominantly composed of anorthosite, are rugged terrains that cover much of its near side. These highlands represent some of the oldest geological formations in the solar system, offering insights into the Moon's early history, including its formation and differentiation processes. 182. The Moon's lunar domes, found in regions like the Marius Hills, are small volcanic features characterized by their steep-sided mounds formed from the eruption of viscous lava flows onto the lunar surface. These domes provide evidence of past volcanic activity on the Moon and offer insights into the behavior and composition of lunar magma. 183. The Moon's impact basins, such as the Imbrium and Oriental basins, are large structures formed by ancient impacts that shaped its surface billions of years ago. These basins exhibit complex features including central peaks, multiple rings, and extensive ejecta blankets, providing valuable clues about the early history and geological evolution of the Moon. 184. The Moon's lunar regolith, consisting of fragmented rock and soil, plays a crucial role in understanding its geological history and surface processes. This layer covers the lunar surface to depths ranging from a few meters to tens of meters and serves as a record of impact events, space weathering processes, and the distribution of volatile elements. 185. The Moon's lunar transient phenomena LTP are unpredictable changes observed on its surface, such as flashes of light or color variations. These phenomena have been reported by astronomers for centuries and remain subjects of scientific inquiry, with proposed explanations including meteoroid impacts, outgassing events, or electrostatic processes affecting surface dust particles. 186. The Moon's lunar swirls, such as those at Mare, Ingenii, and Reiner Gamma, exhibit intricate patterns of brightness and color variations that are not fully understood. These features are hypothesized to result from interactions between the Moon's surface materials, magnetic fields, and micrometeoroid bombardment. Investigating lunar swirls helps scientists unravel the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies like the Moon 187. The Moon's mass concentrations are dense regions beneath its surface that create gravitational anomalies affecting spacecraft orbits. These anomalies, such as those in the Mare Imbrium and Mare Oriental regions, were discovered during lunar orbiting missions and are crucial for precise navigation and planning future lunar exploration missions. 188. The Moon's impact melt breccias are rocks formed from the mixture of melted and resolidified materials during large impact events. These breccias, found in impact craters like Tycho and Copernicus, provide valuable clues about the intense thermal and shock processes that shaped the lunar surface. Studying impact melt breccias helps reconstruct the dynamics of ancient impact events and their effects on planetary bodies. 189. The Moon's lunar highlands, composed mainly of anorthosite, cover a significant portion of its surface and are among the oldest geological features in the solar system, dating back over 4 billion years. These rugged terrains provide insights into the Moon's early history, including its formation processes and differentiation from other planetary bodies. 190. The Moon's lunar exosphere is a thin layer of gases and dust particles extending several hundred kilometers above its surface. This exosphere mainly consists of helium, neon, hydrogen, and argon released from the lunar surface due to solar wind bombardment and radioactive decay of elements within lunar rocks. Studying the lunar exosphere provides insights into volatile transport processes and the interactions between the Moon and its surrounding space environment. 191. The Moon's lunar volcanism, evidenced by volcanic features like lava channels and domes in regions such as the Mare Hills, indicates past volcanic activity that shaped its surface. These volcanic features offer clues about the composition and behavior of lunar magma and the geological processes that operated on the Moon in its early history. 192. The Moon's lunar swirls, such as those at Mare Ingenii and Reiner Gamma, are characterized by their high albedo and distinct patterns that defy simple explanations. These features are hypothesized to result from interactions between the Moon's surface materials, magnetic anomalies, and micrometeoroid bombardment. Understanding lunar swirls helps scientists unravel the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies like the Moon. 193. The Moon's lunar highlands, predominantly composed of anorthosite, are rugged terrains that cover much of its near side. These highlands represent some of the oldest geological formations in the solar system, offering insights into the Moon's early history, including its formation and differentiation processes. 194. The Moon's lunar domes, found in regions like the Mare Hills, are small volcanic features characterized by their steep-sided mounds formed from the eruption of viscous lava flows onto the lunar surface. These domes provide evidence of past volcanic activity on the Moon and offer insights into the behavior and composition of lunar magma. 195. The Moon's impact basins, such as the Imbrium and Oriental basins, are large structures formed by ancient impacts that shaped its surface billions of years ago. These basins exhibit complex features including central peaks, multiple rings, and extensive ejecta blankets, providing valuable clues about the early history and geological evolution of the Moon. 196. The Moon's lunar regolith, consisting of fragmented rock and soil, plays a crucial role in understanding its geological history and surface processes. This layer covers the lunar surface to depths ranging from a few meters to tens of meters and serves as a record of impact events, space weathering processes, and the distribution of volatile elements. 197. The Moon's lunar transient phenomena (LTP) are unpredictable changes observed on its surface, such as flashes of light or color variations. These phenomena have been reported by astronomers for centuries and remain subjects of scientific inquiry, with proposed explanations including meteoroid impacts, outgassing events, or electrostatic processes affecting surface dust particles. 198. The Moon's lunar swirls, such as those at Mare Ingenii and Reiner Gamma, exhibit intricate patterns of brightness and color variations that are not fully understood. These features are hypothesized to result from interactions between the Moon's surface materials, magnetic fields, and micrometeoroid bombardment. Investigating lunar swirls helps scientists unravel the complex interplay of magnetic shielding, surface weathering, and space weathering processes on airless bodies like the Moon. 199. The Moon's mass concentrations are dense regions beneath its surface that create gravitational anomalies affecting spacecraft orbits. These anomalies, such as those in the Mare Imbrium and Mare Oriental regions, were discovered during lunar orbiting missions and are crucial for precise navigation and planning future lunar exploration missions. 200. The Moon's impact melt breccias are rocks formed from the mixture of melted and resolidified materials during large impact events. These breccias, found in impact craters like Tycho and Copernicus, provide valuable clues about the intense thermal and shock processes that shaped the lunar surface. Studying impact melt breccias helps reconstruct the dynamics of ancient impact events and their effects on planetary bodies. These 200 facts cover a wide range of fascinating aspects about the Moon's geology, surface features, history, and scientific significance. In conclusion, exploring the Moon reveals a world rich in geological wonders and scientific mysteries. From its ancient Highlands, composed predominantly of anorthosite and dating back billions of years, to its dynamic volcanic past evidenced by lunar domes and lava channels, the Moon offers insights into planetary evolution that are crucial for understanding our solar system's history. The Moon's impact basins, such as Imbrium and Oriental, bear witness to cataclysmic events that shaped its surface, leaving behind intricate features like central peaks and extensive ejecta blankets. These structures not only provide clues about the Moon's early bombardment history, but also offer a glimpse into planetary formation processes occurring across the cosmos. Lunar swirls, with their enigmatic brightness patterns linked to magnetic anomalies and micrometeoroid bombardment, illustrate the complex interactions between the Moon's surface environment and external forces. Understanding these swirls sheds light on how magnetic shielding and space weathering processes operate on airless bodies, crucial for future lunar exploration and colonization efforts. The Moon's regolith, a layer of fragmented rock and soil resulting from eons of meteoroid impacts, serves as a repository of the Moon's geological timeline. It preserves evidence of impact events, space weathering processes, and volatile element distributions, offering a window into the Moon's dynamic history and potential resources for future lunar missions. Moreover, the Moon's transient phenomena, from flashes of light to color variations, intrigue astronomers and planetary scientists alike, prompting ongoing investigations into their origins and mechanisms. These phenomena underscore the Moon's active role in the solar system's dynamics, influencing our understanding of celestial bodies and their interactions with the space environment. As we continue to study the Moon through robotic missions, human exploration, and advanced telescopic observations, each discovery deepens our appreciation of its significance. Whether unraveling the mysteries of lunar swirls or deciphering the geological signatures embedded in its impact basins, the Moon remains a beacon of scientific inquiry and a testament to humanity's enduring quest for knowledge and exploration. In the coming years, as international efforts converge on lunar exploration and potential habitation, the Moon will continue to inspire generations with its beauty, scientific intrigue, and potential as a stepping stone for future missions to Mars and beyond. As we look to the future, the Moon stands as a testament to the wonders of our universe and the boundless opportunities awaiting those who dare to explore its timeless mysteries. Good night. As we reflect on the moon, our steadfast companion in the vast expanse of space, we are drawn into a tapestry woven with ancient history, geological wonders, and profound scientific mysteries. Its serene presence in the night sky belies a tumultuous past marked by cataclysmic impacts, volcanic eruptions, and the ceaseless bombardment of meteoroids, a testament to the dynamic forces that have shaped not only its surface but also our understanding of planetary evolution. The moon's rugged highlands, cloaked in anorthosite and dating back over 4 billion years, whisper secrets of its formation during the early tumult of our solar system. These ancient terrains bear witness to a time when the moon was a molten world, cooling and solidifying into the rocky landscape we see today. Each crater, from the magnificent Oriental Basin with its concentric rings to the sprawling Imbrium Basin with its towering central peaks, tells a story of cosmic collisions that sculpted its features and left behind a legacy etched in lunar rock. Amidst these geological relics, lunar swirls like those at Mare and Ingenii and Reiner defy conventional explanation with their bright, sinuous patterns. These enigmatic features are thought to arise from interactions between the moon's surface materials, residual magnetic fields, and the relentless pummeling of tiny meteoroids, a delicate dance of forces that paints the lunar canvas with mysteries yet unraveled. Even in the tranquil expanse of its regolith, the moon's surface layer of fragmented rock and soil, we find a chronicle of cosmic history. Eons of meteoroid impacts have pulverized and mixed lunar material, creating a mosaic of minerals and elements that offer insights into the moon's past and potential resources for future exploration. This lunar soil, electrostatically charged and clinging to every surface, holds the key to understanding space weathering processes and the distribution of volatile elements crucial for sustaining future lunar missions. As we bid farewell to another day and gaze upon the moon in its serene majesty, we are reminded of humanity's enduring spirit of exploration and discovery. From the first footsteps of astronauts on its dusty plains to the ongoing robotic missions that uncover its hidden depths, the moon beckons us to push the boundaries of knowledge and chart a course toward a future where lunar outposts may one day stand as symbols of human ingenuity and perseverance. So, as the stars twinkle above and the moon casts its gentle glow upon us, let us embrace the mysteries that lie beyond, fueled by curiosity and guided by the light of exploration. Good night, and may your dreams be as vast and boundless as the cosmic wonders that grace our night sky.